Hello students, Professor Nugent here. In this video we're going to introduce the random effects model. Consider the unobserved effects equation where yit is equal to beta naught plus beta 1 times x1it through beta k times xkit plus ai, which is that unobserved heterogeneity constant to each cross-sectional unit in our panel data, plus UIT, which is the idiosyncratic error. And we have an additional assumption that the covariance between xjit and AI is 0 for all time periods and all explanatory variables. So this is new to our panel data setup. We have, until this point, been coming up with creative ways to get rid of AI because the covariance between the explanatory variables in AI is not 0. And now we're going to change this assumption to allow covariance to be 0. Now, we're going to allow this covariance to be 0, but we will still have serial correlation because AI will be in the composite error, VIT equals AI plus UIT. So AI is in that composite error over time for each cross-sectional unit. And we want to use that information in the composite error. So we can't default back to pooled OLS because pooled OLS will ignore that serial correlation, and so it will not be an efficient estimator. So we need to come up with a way to use the information in the composite error. VIT equals AI plus UIT. So we can think of this error as being equal to VIT. We can define this serial correlation across time in the composite error as follows. The correlation between VIT and VIS is equal to sigma squared A over sigma squared U plus sigma squared A for t not equal to s, where the variance of AI is equal to sigma squared A and the variance of UI is equal to sigma squared U. Alright, so again, pooled OLS is going to ignore that this serial correlation exists. So the standard errors and test statistics are going to be invalid with pooled OLS. What we're going to do is we are going to use a GLS transformation, so a general least squares transformation, that eliminates the serial correlation in the errors. All right, so let's define theta as equal to 1 minus the square root of sigma squared U over sigma squared U plus t times sigma squared A. And this theta is a weight that must be between 0 and 1. Then we can write the, let's keep this on the screen, then we can write the transformed equation as follows. We can write YIT minus theta YI bar, where again we write YI bar as the mean of Y over time for observation for cross-sectional unit Y. This is equal to beta naught times 1 minus theta plus beta 1 times x1 I t minus theta times x1 I bar through beta k x k I t minus theta times x k I bar plus v I t minus theta v I bar. And again, the bar represents the average over time. And this equation, let's write just equation with a star. This equation star is estimated using pooled OLS, and we can do that because this general least squares transformation using the weight theta eliminates the serial correlation. Observe that this equation, we can focus just on one term, is quasi-demeaned. Right? So if theta is a weight between 0 and 1, then we are, in the term that is circled, we are removing a portion of the mean of x1 from the observation. So the random effects transformation subtracts a fraction theta of the mean. Because this is not a complete demean, variables that are constant or change very little over time can be included in the regression. Whilst theta does the work for us, we do need to understand how theta is being estimated. So let's take a look at how this theta is estimated. We can estimate theta as 1 minus the square root of 1 over 1 plus t times sigma squared a hat over sigma squared u hat, where sigma squared a hat, so we're estimating the variance of the unobserved heterogeneity, is equal to n t minus 1 over 2 minus k minus 1 to the power of negative 1 times the sum from I equals 1 to n, sum from t equals 1 to t minus 1, sum from s equals t plus 1 to t of v I t hat v I s hat. Right, so we need the composite errors that are adjacent in time, which is why we have these two summation brackets. We have an error that starts at 1, and then we have an error that starts at 2, and this error stops at t minus 1. This error stops at t, and we want this for all of the observations. And then we have a weight on this. We can then, after we have estimated sigma squared a, estimate sigma squared u hat, which is equal to sigma squared v hat minus sigma squared a hat. So this feasible GLS procedure that uses theta hat in place of theta is called the random effects estimator. And this is what we run in Stata. The random effects estimator, the random effects is consistent and asymptotically normal as n gets large with fixed t under a certain set of assumptions. Stay tuned to the next video. We will discuss the assumptions that we require for the random effects estimator to be consistent and asymptotically normal.